Two subjects that I did not mention there, the other class, they wanted me to do that, is this. Can you write the equation of the shear? Remember, when you do the shear and moment diagram, you do not need any equation. Everybody understand that. Actually, in ME 218, I asked a student not to do it. I tell you why. In this class, in a week time or 2 week time, we are going to spend about 2-3 weeks doing that. But we do that not for determinate problem. We do that for determinate problem. Our goal is to get into indeterminate problem. What is indeterminate problem? Indeterminate problem, there are too many support there. Everybody understand that. If there are too many support, static is not sufficient to solve for the reaction. Correct? If there is no reaction, there is no shear diagram, there is no. How are we going to solve it? There is only one method to be able to solve it. That's by writing the equation of shear and moment, everybody. So if there is a equation in some of your homework, I hope that you notice, to write the equation is for that purpose, to get you ready for the following week, or week 3 or week 4 here. Everybody understand what I'm saying that? Are you okay with that? Because everybody on the other class said, okay, but eventually I did one part of the problem, so I'm going to do the same thing here, because some of you may need a little bit help there. But look what happened there. We had a beam like this, so I'm going to I put this up there, so let's put that. We had a beam like that, which had a 15, this is what we had before. We had 1,500 pound load there. We have 1,000 pound-foot of moment there. And we had here a load, uniform load of 250 pounds per foot. And the dimension was given, if this is what we did last time. This was 5 feet, 5 feet, and 10 feet. Is that correct or not? Yes? Then when we draw, I'm not going to repeat that. These are all in your hand, in your notes. So you don't have to rewrite this, please. Look at your note. They are there. So don't waste your, I have to put it here, unfortunately, because I ran out of time. And every time this happens, I have to spend more time doing that. Then this reaction, I believe, was 1,800 pounds. And the other reaction was 2,200 pounds. So this one was 2,200 pounds. And then when we draw the free body, the shear diagram, we started with 1,800 pounds. This is in pound, that's the shear diagram. We went to this point, and epsilon before still is 1,800, and epsilon after, suddenly 1,500 appears there. So we went down to 300. Then we went straight to point. This was point A, this was point B, this is point C and D. The same thing here, A, B, C, and D. So you bring those points down. So we went up here. Then from there on, we went with the rate of 250 per pound. So we end up like this, minus 2,200. Then went up 2,200, back to 0. This was our shear diagram. It is in your note. You don't have to redraw that. I'm redrawing that because we want to discuss that. Then for the moment diagram, we have to do the same thing. For A, B, C, and D. So you can use different method. One method we used was the area method. So this is plus, this is plus, this is plus, and this is minus. And we went up to, as I recall, if you look at your note, we went this much plus, which was 9,000. Is that correct or not? Yes or no? Yes. Right? And then we went a little bit further, which was this much, 300 times was or 1,500. So we went up to, down, no, okay, sorry. We went down 1,500 first, so we went to 1,000, that's right. So we went to 8,000, correct? So down 1,000 to 8,000. Then we went 1,500 up, which took us to that point, which was 9,500, correct. And then we have to add this little. We find the location of that one. We are not going to do that again. It went up to 9,680, which was this point E. That's what we did last time. And then we went D0. That was our. The two question which takes a few minutes to answer that is this. If I want to write, which I don't need, notice I draw the shear and moment diagram without using any equation. Everybody understands that. However, for future lecture in this class, we need the equation of the shear and moment for different purpose. Is that correct or not? That's what I'm. Can we write the equation of shear and moment for the different part of this beam? First of all, how many parts do we have? 3. Everybody see what I'm talking about. Why 3? Because this is very important to recognize that. Anytime the new load comes into the system changes. Notice this has a different scenario here. So the way we want to look at it, it's just 3 parts. So let's call it green part. This is green, which correspond to this line. Is that this is the moment between what? Between A to B. X between 0 to 5. Then there is another set here, which is maroon part, I call it, which is B to C. Notice there is a break here. Is that correct or not? So that is represent X between 5 to 10. Is that correct or not? Now, why 5 to 10? Remember, some of you in ME 218, I asked you to write the equation of that part. You call this one X. That's wrong. When you choose the center of coordinate, the center of coordinate not keep changing. Is that correct or not? Look what I'm saying, that if this is your X direction and this is the Y, where is X equal to 0? A is X equal to 0. B is X equal to 5. This is 10, and that is 20. You cannot keep change X. You can, but that's for different reason. Is that correct or not? So let's stick to the same system of coordinate. And the third one, which is here, the third one, which is a little bit more difficult than the other one, will be what? Which will be this parabola and this. Now, in the final, I had asked that question from a couple of students. Are you with me? Yes? Okay. And this is what they did. One particular, if even he's here, was it Mr. Nazarian is here? Yeah, you are back there. You remember what you did. Actually, I gave you credit. Oh, remember. Now, you have the coordinate of this point. You have a coordinate point. Of course, everybody who has seen math, he can write an equation for that line. Yes or no? Is that what I'm asking you to do? No. Because when it gets to indeterminate problem, you don't have that line. That's the whole idea here. So what I asked you to do, which you didn't do that, but you get credit for me, you are requesting that you have half a page you wrote for me, which was correct. The way he was doing was correct, but that's not the idea. I spent half of my life doing this, by the way. I want you to know this is my research area. So I know a lot of tricks about this system, and I'm going to show you all those tricks when we get there. This is the establishment of a computer program for solving all the indeterminate problems, like a frame of a building or frame of an airplane or frame of, which has 100 or 150 unknown. Everybody understand what I'm talking about. Therefore, we are going to get there, at least partially, to see how this is being done for indeterminate problem. Therefore, all I want you to do is do what I asked you to do using the equilibrium method. Is that correct or not? Equilibrium method is this. If I want the equation of this line, I do not go fit a curve here. Everybody understand that I cut the beam somewhere between A to B, and I draw a little free body diagram. For part, maroon part, I have to cut the beam somewhere between B to C, and for this part, I have to cut the beam somewhere between C to D. Since this one is the more difficult one, and I'm going to do that one for you. Is that correct? Or I'm going to write the equation of the shear and moment based on the static equilibrium of what we have expected from you to do. We come up with this equation, and that equation, while your X and Y are here. Everybody understand that? This is X, and this is M, and that is X, this is shear. Is that correct or not? Yes? All right, so what do we need to do that? In order to do that, I just let me put this up, then I can put it down again. So let's this one go up a little bit. So I need this board. Okay, I hope that works there. All you need is the free body diagram from point A to this point that you cut it. Is that correct or not? Let's do that. So here it is your beam. So you pass point A. This is point B. Let's put it here, which you have that force and that moment, 1,500 pound and 1,000 pound-foot. Here you have the reaction of 1,800 pound. And then here somewhere, this is point C. Let's make this a little bit smaller. And you have this load sitting here. But you have not reached to the D, everybody. And look where the cut is. The cut is somewhere between between C to D, or between 10 to 20. In other words, if I want to use the color coding, X now changes between 10 feet to 20 feet. Is that correct or not? Yes? Because 0 is here. I'm between here to this region. And remember, I'm going to put, these are all internal, shear as a function of X, as M as a function. I call it blue because I need this blue line. Yes? Now, what is X? Where is X? Now, some of you in ME218, remember, if you won't come back again, look at your final, you will see that. You call this distance X because you thought I'm talking about CD. I asked you to write the equation for CD, but remember, X equal to 0 is here. Is that correct or not? Therefore, according to this system, what is X? This is X. Is that correct or not? Yes? Because center of coordinate still is at A, correct? Unless you want to change it and put your center of coordinate here, that's a different story. Is that correct or not? But center of coordinate, you usually keep it as it was before. Is that correct or not? Yes? All right. Now, look what happened here. Now, the rest of the story has nothing to do with ME218 or nothing to do with ME219, actually. This is a static. Everybody in a static class, now, if this is there, you give it to anybody who has gone through a static for 2, 3, 4 weeks, should be able to write sigma Fy equal to 0 and sigma M equal to 0. Yes or no? Which has nothing to do with this sign convention, anything. So when I write sigma Fy, please write it down, equal to 0. Any force going up is positive. Any force going down is as static people do. Is that correct or not? Yes? So I go here. This one is up, so it is 1,800 up. Yes or no? But this one is down minus 1,500. How much load is that? Remember, the magnitude of that, the distributed load of 250 pounds per foot. How many foot is this? Everybody see what we are talking about? That's not X. That is X minus 10. Yes or no? Whatever X is, remember, X cannot be less than 10. So X is always larger than 10. So if you are at point 13, this is 13 minus 10. Is that correct or not? Or X minus 10? Absolutely. So the amount of load, imaginary load, that you would put here is 250 times X minus 10. Agreed or not? Yes or no? Correct? Those are your loading system. Then I put here minus 250 times X minus 10. That minus shear equal to 0. Everybody understand what I'm talking about? Yes? So therefore, you just, because this is negative, this is negative, this is negative, the only one positive is this one, according to a static. Then you write shear as a function of X equal to, you take it to the other side, these two become 300 minus 250 X minus 10. Now, the first clue. Here, I don't care, but I tell you, when we get 2, 3 weeks, when we get there, never expand this. Leave it like that. These are one of those tricks that you should use in order your final answer become very simple. Do not expand that. You leave it in the parentheses form. Again, don't worry about it for time being. When we get to this system, I will talk about it in detail with you. Now, is this the equation of this line, blue line? Of course it is. Yes or no? Look, I cannot put here X equal to 1. Everybody understand that? I cannot put X equal to 7 or 9. I can put here X equal to 10 and above. Let's check it. If I put X equal to 10, look, if you don't expand it, this is much simpler. If I put X equal to 10, this value become equal to 0. The value is how much? Is that what's showing you here, equal to 300? Yes or no? At x equal to 20, if you put here 20, the x become minus 20. As a matter of fact, you can set this equal to 0 to find out where x become equal to, when the shear become equal to 0. But that's the equation of that right without using the coordinate system. Do you understand that? This is the method we are going to use for indeterminate problem. Yes or no? Okay. Now, can I use the moment? Find the moment there. This was finding the shear, and that equation was. Now, moment, you cannot do that. Moment, you have to use this system. Is that correct? Now, what you did the integration. The integration of that for this problem doesn't work unless you use this constant of integration, which is a little bit different. Look, forget about all those things. Use the equilibrium again. Equilibrium like a static. Now, sigma m about a point equal to 0. Where do you want to take the moment about? You tell me. Is it A or is it this point? Which one is better? That point, because the shear, you want to get rid of that shear. If you take the moment about here, you have to take the shear times x, mx, etc., etc. Usually in ME2 static, we always take the moment about A. In a strength, we always take the moment about the cut. Everybody under that's the difference. So yes, you are right. At section XX, let's call that section XX or AA or whatever you want to call it. So the moment about that point equal to 0, which become the following. So look at this. This is again a static. 1800 times x, positive or negative? Negative, obviously. Then 1500 times what? 1500 times this distance, which is, come on guys, be quick. X minus 5, that's right. X minus 5. Is it plus or minus? Plus. How about this guy here? This is going counterclockwise, therefore it is plus 1000. Yes or no? Come on, this is plus, this is plus, yes, that's plus, this is minus. Is that correct? This goes clockwise, these two go counterclockwise, yes? Then come to this one. This is also plus, yes or no? Plus what? 250 times x minus 10, that's the load. What's this distance? X minus 10 divided by 2, yes or no? Because this was x minus 10. This distance, write it down. X minus 10 divided by 2. Is that correct or not? Therefore, this becomes always like that. It becomes something routine that I show you again later on. 250 x minus 10 to the power of 2 over 2, and that one is also plus. And then plus mx equal to 0, or mx, which I put it up here somewhere. I better put it here. Mx equal to, you take it to the other side. So it becomes 1800 x minus 1500 times x minus 5 and minus 1000 and minus 250 times x minus 10 to the power of 2 over 2. Anyhow, that is the equation of that parabola, which started at this point and end at that point. You can check it yourself at home. Now, don't expand it again. Leave it as it is. Is that correct or not? Yes? Because I want to check your free body diagram. But there is a reason for it. As I said, I will explain it to you. Everybody understood what I did here? Yes?
Are you going to explain why it's squared and over 2, or is it?
Yeah, because the load itself was how much? The load is how much? If this was the load P, and this distance is whatever A, this is A divided by 2. Yes or no? What was this distance? X minus 10. So what's half of that? X minus 10 divided. Then what is the load? 250 times. Then times this. So it becomes. By the way, this goes higher and higher. You don't know yet. This is going to be to the power of 3 over 6, to the power of 4 over 24, to the power of 5 over 20. You get there. Don't worry about it. This routine is some routine that I was talking about. This is going to happen for more complex problems. And we are going to do that in this class. Everybody understand that? This is a very simple case of it. Is that correct or not? But you have to do it this time, Mr. Nazarian. I hope you understand. Because you did the other one so nicely, I'm sure you can do this one. Is that correct or not? Yes? By using equilibrium, correct? Not, but look, direct integration doesn't work. Direct integration of this one is what? 300 times x, which we have it here, 1,500 minus. But there is a constant of how much here? 5 times 1,500. Everybody understand that? Then this becomes minus 250 x minus 10 to the power of over 2. But there are lots of other items there. That comes from constant of integration. And unless we learn that properly, we cannot do that. Everybody understand that? Yes? However, equilibrium will give you, why do you want to use the integration? I don't suggest it for time being. Not yet, unless we go through the whole system. Is that correct one? Yeah? Anyhow, so for this one and this one, so easy, I don't have to tell you because you end up with this line and this one, which is easy. Is that correct or not? Yes? You have to cut between 0 to 5, then between 5 to 10, but the most important answer you gave me, which is just 3 parts. Is that correct or not? The more load we have, the more. Then the next question that I will ask you is the design. Everybody can design this beam. Remember, I gave you some homework. Yes? Okay, let's go to the design of that. Now, this is not the complete design. We are going in a week time. Again, we are going to have the more complete design of the beam and shaft, but this is the moment diagram is sitting there. What's the maximum moment? 9,680. Then this is what we do. So please write it down. This is just the highlight because I explained that for other class. I might as well. M given 9,680 what? You need a unit. Look at the unit. This is the mistake that everybody makes. Sometimes there are kips foot, sometimes there are pound foot, pound inch, etc., etc. What did we use there? Pound foot. Very good. So pound, I want you to pay attention to all of that. Pound foot. Then depends what you are designing. That's the maximum moment. If I make it safe for this one, then everywhere else is going to be safe. Yes or no? Now, you may choose, let's say, a wooden cross-section, rectangle. This is just a rectangular cross-section. So if you choose a rectangular cross-section for this beam, and the cross-section of beam has a moment like that, because positive moment is 9,680, tension, compression on top, tension on the bottom. It is symmetrical, so all you need to calculate is sigma. Sigma equal to what? Sigma equal to MC over I, because it is on top and bottom is the highest value. And since this is a rectangular cross-section, the rectangular cross-section have a I equal to 1/12 of, let's call this W and call this one H. So W times H to the power of 3. And the C is equal to H over 2. Is that correct or not? So you have 2 variables, the width of the beam and the height of the beam. One of them should be given to you. You cannot solve that for two unknowns. So what they would give you is sigma allowable. Now, this is sigma equal to MC over I, but this is in reverse. So that if this is the wood or a steel, let's say this was a steel, and sigma was given equal to 12 KSI. What does this mean? Sigma allowable, I'm sorry. Sigma allowable equal to 12 KSI. What does it mean? Sigma yield is for a steel. If this was made of a steel, sigma yield of a steel, remember from ME 218, was 36 KSI, yes or no? Remember from Hooke's law? So that means we have a factor of safety of 3. Is that correct? 36 KSI divided by 3 gives me a sigma allowable of 12 KSI with a factor of safety of 3. Sometimes that changes from, of course, in real life scenario. So therefore, I have the sigma, I have the M. What I need is I and C, but I and C will be dependent on W and H. But I have to decide on one in order to find the other. Let's say if W is 4 inch, then I will find the H. Is that correct or not? Or I assume H equal to 12 inch, then I find the width of the beam. Is that correct? And sometimes they do reverse. They give you some ratio. I don't know in none of your homework how they was that. If, for example, if I tell you, if, this is the question, if I give you, for example, H equal to 2W, so we are using a ratio of 2 to 1. Everybody understand that? Height is 2, twice as length. Then you can solve for W. Is that correct or not? Because H become equal to 2W, so the only unknown is the value of W. Is that correct or not? Yes? Correct? Yes. One of your homework, I believe, is like that. Is that correct? Yeah. All right, so you have done that, right? Now, what about if you want to choose another homework I gave you, a white flange beam? Are you familiar with that one? Just because I'm not sure whether everybody has, I just want everybody to be on the same level. White flange beam. You know what the white flange beam are? Yes? No? Did you go through ME218? You must have. So here it is. So I'm having a few extra copy. Those of you who have your book, please go to page 17 or 19. 17 and 19, I guess both of them will do. Let's see, which one do we want? 19, page 19. I have few extra pages here for those of you who do not have those pages. No, this is metric system. No, this doesn't work. So anybody needs, just you share it three together. It's out there. So, okay, I have only few, guys. If you have your book or you have your book, go to appendix page 19 and page 20, two, three more here. You can share it if you have your calculator or computer with each other, so please share it, so we'll go there. Anybody else here need one? Need? Oh, you have it there. One more I have here. Okay, this is what we do, guys. This was the rectangular section. It's very simple. This is not a total design. There is more into that, and then we get a little bit past this Mohr circuit, etc. I'm going to discuss that later on with you. Now, this time we want sigma allowable given is still equal to 12 KSI, but then we want to choose one of this section. We call them white. This is flange. This is stem, and then this is called wider because it is wider. Sometimes they are smaller. They call it S shape. So this is white flange. W, they call it W, or sometimes WF. So old book, they call it white flange. Now the new book, they only call it W section. Anyhow, it is given in the table in the back of the book, but you have many choices. You can choose a beam which is much taller and narrower, or you can choose a beam which is more compact, so you need certain I. Is that correct or not? However, the point is you need an I, you need a C, and I and C depends on the shape. Everybody understands that. And it is not simple to find because it's not like rectangular page that I can go ratio of 2 to 1 or 3 to 1. Everybody understands it? Yes? So what we do is the following, which you have probably remember from ME218. We make that equation to look like that. Sigma equal to M divided by S. S, where S is equal to I over the C. Is that correct? So what's the unit of S? Unit of S is, come on, length to the power of 4 divided by length. So it is length to the power of 3. So it will be either in inch to the power of 3 or millimeter to the power of 3. We rarely express it in meter to the power of 3 because this is the cross section. So there are tables in the back of the book with the S value given for each cross section. So all you have to do, calculate your S value here. Now this is what we do. 12 KSI equal to M. M equal to what? 6,000 or 9,000, how much was it? 9,680 divided by S. And that was pound-foot. Now, I did this in the final. Many people use it exactly what this. Totally wrong. You did not. If you do that like that, everything goes wrong. Why? Because we are not using the correct unit. Everybody understand that. Notice, first of all, this is pound. This is kips. Kips 1,000 pounds. Therefore, first thing you should do, multiply that by 10 to the power of 3, so that become PSI. So you watch always in this class, especially see, in ME218, I'll let it go because you were sort of beginner of a designer. Now you are intermediate designer, okay? You are getting close to the outside world, so please be careful of what you are doing. Is that correct or not? Yes? So therefore, still is not 4. This is pound per inch square. This is inch, so this is in foot. So I have to multiply this by 12 as well. So please be careful. Times 12, so that becomes pound inch. As you see, the result will be in inch to the power of 3. So when you solve that, S become 9.68 inch to the power of 3. So that is what the require S's. So if you go to the table that I gave you or to the page 19 or 20 in your table, choose a section. Now, I remember last year in one of the final in ME 219 when I gave that, somebody went to the top of the table and for this beam, choose me a beam this height. Everybody understand that? That's a no-no. So as I said it in the other class, we have to start from smaller section because of course if I needed this much height and you give me 2 meter height or 20, 30 inches height, of course that's going to work. But somebody is going to fire you the next day if you are working for a company. Is that correct or not? Yes? You want to find the most economical section, means the smaller section that is followed. So you start from the bottom of the page. You go to that shape, you are there, the S value are given, but you don't start from top. You go from the bottom. You see the minimum is how much? 5 point. Everybody see that in the bottom of the page? Page 19. You see the value is how much? 5 point. Is that good section? Of course it's not. So you go up. You go up. Which one is qualified? 8 is not good, but 10 is good. Yes or no? 10 is larger than that because this is the minimum required. Anything larger than that is stronger. Anything less than that is weaker section. Yes or no? Because S is representing the I. Is that correct or not? Yes? Are you following there? Are you having the table there? Yeah, share it. Okay, okay. So you go down, so you see that a W5 what? What is that? There is a number next to it. Please read it. 5. I have it here. I just want you to do that because 5 what? 19. Good. So let me get my solution here to show it to you as well. Okay. I had it here. It must be here somewhere. Okay, yeah. 5. All right, 519, correct. So 519. Now, those of you who are aware of that, what is 5, what's 19? The 5 is approximate height in inch. 19 is the weight per foot. So this profile is going to have 5-inch height. So if you are designing for a car or something, so you don't want to go more than 5 inch, so that's the height of the beam. The weight of the beam is 19 pounds per foot. You have to pay per pound. And the S value is a little bit larger than this, so you are okay. Is that correct or not? Yes? But is that the only option, or you have other option? Go now to the 6-inch height. What do you see in the 6th level? 6th level is 16. There is another option. W6, 16. Which one is more economical? Of course, the 16, because it gives you, of course, you have to pay a little bit because this is a little bit higher in height, but the weight is much less. So if you are concerned about the weight of your structure, you want to make a light car or whatever, or boat or whatever, you use this one. Is that correct or not? But you need to put a little bit height there. Sometimes height is the restriction, sometimes weight is the restriction, depend on the criteria of design. Is that correct or not? Yes? However, if nothing else is said, 16 is better than 19 because it's less weight, it's less stress too. Is that correct or not? Is there another choice do you have? Yeah. W8 what? 13? Good. So I think between these three, of course, this is the lightest one, but it's a little bit higher. Is that correct or not? So you have no height restriction. That will be your answer. Is that correct or not? Actually, the next one is there too, 10 and 15, but that gets more weight. Is that correct? So no good. Is that correct or not? So that was the idea. So you always find S. S will be in inch to the power of 3. On the other table, on the other side of your book, are millimeters. So they are all expressed in millimeter to the power of 3 or 6. Everybody see that? And you want SX, you don't want SY. This is SX. The other one is SY because you are putting your beam this way. Is that correct or not? Anyhow, these 2 points also were in your homework, so I thought need a little bit review. So that will cover all your homework. Is that correct or not? Yes? Now let's start with the last chapter of your review. The last chapter, of course, is chapter 7. We are talking about what? Talking about the Mohr circle. So good. So that's why one need to put this. I don't have to go into details. So Let's put that one down again. Okay. Now, remember the handout that I gave you? I just put it here because it's just simple to follow. What we discuss is the following. First is we have to come up with the state of stress. You know what the state of stress is? That's the state when you have sigma x, sigma y, and tau xy, which comes from the 6th chapter that we learned, chapter 1, 2, 3, 4, 5, and 6. You end up with the state of stress. Could look anything. In this beam, we have a state of stress. So any part of machine design that you do, let's say you are talking about a sort of a wheel of a machine or an airplane or whatever, and you end up with lots of load there and eventually end up with a state of stress like this. So this is the idea, sigma x. You may or may have sigma x or may not. It could be in tension or in compression. Then you may or may not have sigma y, especially when you are talking about a plate. If it is a plate, which is the bumper of your car, the door of your car, the side of an airplane, any plane that you see, most of the items are not like a rod. They are having dimension x and y. Is that correct or not? So we go like that. So you may have sigma x and sigma y. You have to go through chapter 1 to chapter 6 to come up with this. Everybody knows what the sigma is. Sigma is next page. So if I go to next page, you will see what happened. So the next page, here it is. All the state of it. For the beam, we talk about it. Sigma equal to what? P over A. Is that correct or not? Yes. And MC over I. Yes or no? Correct? And it's the U. But the shear, it's only because there is no torsion in the beam. The shear is only chapter 6, which is VQ over IT. Then we went to the further, so there is a shear stress as well here. So that's what I'm saying that. Now, going to a 3D object, which you mechanical engineers usually do, that's why ME 218 is all for every engineer, like civil engineers. Civil engineer basically, if they don't go to graduate school, all they do is the design of the shear and the beam and the column, which is really is two-dimensional. Everybody understands that. But you mechanical engineer, all the objects are 3D. You are designing a piece of equipment which goes like that, and you are loading it at one corner. You have to be more careful. We call them still beam, but it is much more complicated. Everybody, actually mechanical engineer, their design is much more complex than a civil engineer. Everybody understand what I'm saying there. Therefore, we go to the bottom of this page, and you see that this one doesn't work, so I don't know whether it works or not, so no, I don't think so. So let's go down a little bit. You see that equation. Oops, sorry. I wanted to go bottom of the page here. Here we go. You see that those equations, we talk about it. Is that correct or not? Because you have the torsion, you have the sigma equal to m, you have to do bending. We talked about it in detail last week. Is that correct or not? Yes? Everybody is familiar with it. But nevertheless, you end up eventually with a sigma x, sigma y, and tau xy going through the system. Then what happened there in this scenario, what I did for student in ME 218, because this handout was given to ME 218, but I modified that a little bit for 219 there. You see, this is the state of stress in general. Then this were the problem that I gave you, and we did it together here. And then go to page 6 now, or page 5. I'm sorry, that's page 5, which is the typical problem, which again, I did it for you guys in ME 218, but some of you who were not in my class, probably you have seen some other version of that one. This is a drill pipe. Is that correct or not? Yes? On a drill pipe, you have a system like that. Okay, this pen is no good, so let's get rid of it. Okay, so there is a drill pipe there. So let me advise as I put it here. So here is a drill pipe. So in order to have a drill here, you push it down with a force P, but you have to put a torque there to twist it. Is that correct or not? I did this problem for all students there. I put it a value there. The value of the torque is 500 pound-foot. The value of P is given there, 5,000 pounds. Everybody see that? And there is a pipe similar to this. So it is 2 inches in diameter, 2.5 inches in here in diameter with a thickness of 1/4 of an inch. Everybody understand that? Then I asked the student, which I'm sure all of you can do, to find out the state of stress there. Is that correct or not? The state of stress there, as we discussed it last week, you have to cut here. You have to put the internal there. The internal is normal stress and the shear stress. Is that correct or not? Normal stress, sigma, equal to minus P over A. Yes or no? Correct or not? Yes? Tau equal to what? What kind of tau do we have? Tau is the torque. It's a torsion. Yes or no? Tau equal to TC over J. You have gone through that, so you have the cross-section. That's the result. I don't have to do it again. This is the understand. This is your handout. You can study it at home. I'm just bringing it up for those of you who haven't seen this problem. This is how we do it. Is that correct or not? Yes? So at this point, if I cut it here, I have to come up with the state of stress like that. That's the torque. So I have a torque here, and I have a P there, and I have the tau there. Is that correct or not? So the state of stress looks something like that. At this point, let's say point A, you end up with this one, 2,820 going down. Why? Because it is in compression. Yes or no? In the y direction. Correct? And there is a shear force going like that, right? This is the shear force, tau equal to TC over J, which goes like that. Is that correct? This is the square there. Is that correct or not? Yes? So that's the state of stress. So you calculate that one, you calculate that one. It's all there. You see that this one is 2,008 minus 2,820, and the other one is 3,320. Of course, you calculate the J of the cross-section, which is J of outside minus J of inside. All of you know that. Is that correct or not? Yes? This is a very simple problem compared to some of the homework I gave you. However, this proves the point that this is 3,320. Now, what comes next is the review of chapter 7. Is that correct? This is the state of stress. Remember in page 1, I said the state of stress. This is the state of stress. It could be any shape. This is one format of it. In general, we'll be looking like that. This is for this particular problem, which is a little bit simpler. Is that correct or not? For every other problem in future, you are designing anything, part of an airplane, as I said, part of machine design, whatever, you come up with system like that, going through chapter 1 to 6. You have to do it. Now come to chapter 7, which is very important, is this. That's why I have this pipe here, see, to show you, stress the point here. Look, this is a pipe similar to that drill, yes or no? Look how it's being constructed. Everybody see where the glues are? The glues are not along the X and Y. What did we calculate here? You see, we calculate this is state of stress. Yes or no? This is X, this is Y. X happened to be compressive force because I was pushing it. 2,820, yes or no? PSI, and the torsion give me a shear stress going like that. Is that correct or not? 3,320. Suddenly, if I see that this system, I said, oh, I have to put glue here. I want to find what kind of glue do I want here. Wouldn't you be interested to find what kind of stresses are along this direction? Is this direction of X? No. Is it direction of the Y? No. But it is somehow shifted, yes or no? How much shift do I have? I have to give you. This could be 10 degree, 15 degree, or whatever. Is that correct? Or that will be given to you. Therefore, what this question is, now that I found the stresses along the X axis and Y-axis, would I be interested to find the stresses along that surface? Yes or no? That surface is not parallel to X. It is parallel to X prime. Yes or no? Correct? So in general, we call it transformation of stress. This is chapter 7 title is transformation of stress. Why? We are going from X and Y to X prime and Y prime. And the shift is this way. Is that correct or not? Yes? Everybody see what happened here. Here is your X. Is that correct or not? If I go in this direction is the direction of the welt and perpendicular to direction. That is what the idea of chapter 7 is. Is that correct or not? Now, how do I get that? You already have few sample in the past, so which is the next page. So you go to the next page. You want to study this by yourself, guys, so you go to the next page. You will see this. We did that in ME 218. I'm sure in every class your instructor have done that. The first thing that we do as a teacher of ME 218, we do this. We get a rod like that under this. What is this? This is lecture 1, ME 218. Yes or no? Sigma equal to what? Sigma equal to P over A. Where? That's very important. Where I cut it like that. Is that correct or not? So if I look at this point, that point gets sigma equal to P over A. Everybody understand what? Because the cross section perpendicular to the x-axis. Yes or no? So if this was a wood and it was a grain like that, wouldn't you be interested to find the stresses along the grain of the wood? Have you done this problem in ME 218? We did in our class. I'm sure all of you who were in other ME 218 must have, your instructor might have done that. Is that correct or not? So they ask you to find stresses in that direction. Is that correct or not? Yes? Now if you turn this around, that's the same problem. Everybody see that? Yes? Look, guys, is this the same problem? Yeah. Right. The only difference here, we have only one sigma. There, what do we have? We have one sigma and we have one shear. It's more complicated. This is that. So when we were there, we can use geometry to come up with the stresses in the x prime direction and y prime direction. Actually, I did it. Some of you recall, I end up with these two equations. Remember that? Cosine square theta and sine theta, cosine theta. Is that correct or not? Yes? Some instructor just use the number because the solution manual shows only the number, not the equation. But I purposely give you the equation to see that I can do that based on the theta. Is that correct or not? So theta changes from 5 degree to 10 degree or 15 degree. Still, that's the answer. But that is only for sigma equal to P over A. Yes or no? Now, if I have a shear scenario, look at this one. This is the torsion scenario. I can find the same thing here, find the stresses at that angle. Look, this is what exactly I have done here. Everybody understand that? And this one has normal stress and shear stress. Do we have to do that every time? No. What happened that in ME 218, in the book, they went through this process. They actually didn't look at this small problem or this problem. They took this and find the stresses in the x prime and y for all three of them, which is the general case. Is that correct? You don't have to do that. They have done it for you. Is that correct? But you can study that in the book, beginning of chapter 7, few pages. You go to this page 1 and 2 and 3. And finally, when they did that, which I have to go a little bit down further to this, in this page, exactly. This is for pure sigma. The second one is pure tau, and the last one is for all three of them. When we do that, this is what we get. This is the combination of all three of them. Everybody see that? Yes? Actually, as you see, sigma x cosine square again appearing here. That one is appearing here. Everybody see that? That is the effect of sigma x. That is the effect of sigma y, and that is the effect of tau. Everybody see that? So if this tau and this one become 0, sigma x become the problem number 1. Everybody understand that? If this and this 0, that's problem number 2. But what I'm saying that you don't have to worry about it. You don't have to learn the process because the process is very tedious and you have to write lots of sigma fx, sigma fy. But what is the point is this. What these two equations represent. Sigma x prime and tau x, isn't that what you were looking for? Yes or no? The only thing that you have to be careful, first, it ends up like that, but Mr. Mohr didn't like it like that. He changed the format of it. End up the format of these two by changing the 2 sine theta, cosine theta into sine 2 theta and replacing this in the form of cosine 2 theta, sine 2 theta. He changed it, and then it become unfamiliar. So what he did is the next page. Look at what he did. These two equations end up to equation, next page. Look at that one. Equation 7567677. That's all you have to do. Put that in a box. Please put everybody. If you have done it in ME 218, this is all you have to do, nothing else. If you want to calculate stresses, write it down in the direction of the x prime y prime. These are the three equations, includes all three of them. So used, in other words, the answer is, if I ask you to find out the stresses in any other direction, you use this equation of 5, 6, and 7 to calculate sigma x prime, sigma y prime, and tau x prime. Actually, I did that in the handout. Look what I did. I used the three equations. Go a little bit further. If you go down there, that's what I did. I used these three equations. The original state of stress, look at it. The original state of stress, sigma x equal to how much? Sigma x equal to 0. Yes or no? Come on, guys. Is this sigma x there? No sigma x there. Sigma y is equal to how much? Minus 2,820. I can use this one, I guess, I suppose. So here we go. And tau xy is how much? 3,320. Now, when I go to, so that degree, I went how much? I went 22.5 degree. Do you see that? Yes? So in other words, if this is the x, I went how many degree here? This direction of the glue is at 22.5 degree. All I have to do, use these three equations, put theta equal to 22.5, and sigma x equal to 0, sigma y equal to that number, and I did that, and I get that one. Yes, I did that in detail. So if you haven't seen this problem, some of you who were not in my ME 218 class, all you have to do, put these three numbers in that three equation, that's what you get. Is that simple as that? Is that correct or not? Yes?
I think I asked this last quarter too, but I can't remember. In the sigma x and sigma y, respectively, the cosine 2 theta you see up there, is that denominator or numerator?
Let me see.
The cosine 2 theta and sigma x, is that denominator or numerator?
No, it is the numerator. It is sigma x minus sigma y divided by 2. I'm sorry, it is multiplied by cosine 2 theta. So I couldn't write it any other way here. Is that correct? I understand. It looks like that is divided by 2 cosine 2 theta. No, it is, I don't know how I'd say, sigma x minus sigma y divided by 2 multiplied by cosine of 2 theta. Everybody understand what the question is, but it is in your book anyway, more better. Is that correct? It's not denominator, it's numerator. In the other class, they were saying the same thing. I just told them laughingly, you make the correction yourself. Is that correct or not? Yes? Actually, this is sigma x minus sigma y divided by 2, the whole thing multiplied by cosine of 2 theta. Everybody understand what I'm saying? But you don't use this one, use the one in the book. Is that correct or not? Yes? All right, but that's the point. Look what we get. Now, if somebody asks you what are the stresses along the glue, which one of them? You see, in ME 218, this was not required. In ME 219, this is required. Now, what are the stresses along the glue? Come on, guys, look at the picture. Is it x prime or is it y prime? Which one do you need? Where is the glue? Look at it. Look at, is the glue this way or the glue is this way? I showed you here. Isn't that the direction of the glue? Yes or no? What's the shear in the glue? We should usually glue work for the shear. What's the value of the shear? Tau, x prime, y prime. How much that is? 1,350. Is there a normal stress perpendicular to that? Yes or no? How much that normal stress? It's not sigma x prime. It is sigma y prime. Everybody understand that? Because you have one direction here, one direction here. We don't care about that. This was the glue part. Yes or no? So if you are welding a part of a structure in mechanical engineering design, you need this welding or this one, you have to be careful what you are doing that. And many times you have to do that to find the stresses in different directions. Is that correct or not? Yes? Everybody with me? Okay, so that's why this becomes a little bit more advanced than what you learn in ME 218. That's why I really spend a week trying to review this stuff with you if you are listening, of course. If you know this stuff, then you get bored and you look at something else. Is that correct? Bear with me, okay? All right, maybe I gave you some hint here and there. Did you see what I'm talking about? This is the stresses in this direction, correct or not? Yes, which is sigma y prime. Now, what happened here? Can you tell me? Are the stresses changed or not? You see here, I put increase, decrease. Everybody see that? Which one of this is more critical, you think, for the normal stress? Here, normal stress was how much? 2,820. What's the normal stress here? Is 4,000. This is much more critical for material. It's the same material, the same point, the same spot, but the stresses here is much important than vertical. Yes or no? Okay, if this is changing, then wouldn't that, this was for 22.5 degrees. If I change that to 30 degrees, 40 degrees, I keep changing. Is that correct? So how do I get the maximum? Of course, everybody knows the answer there. How do I get the maximum? Mr. Mohr turned in these two equations, 5 and 6, by eliminating theta from the two equations. He turned that into a circle. So the stresses, all the stresses from 0 degree, which is this one. This is theta equal to 0 degree, to 180 degree, which is back again to the normal. All of them become on the circumference of a circle. That circle shows you everything. Is that correct or not? And it shows you the maximum stresses. It shows you the principal stresses, which are, we call it principal stress, the maximum shear, etc., etc. Yes or no? Correct? Let's do that for an example. So that's beside the point. So we are going to do this problem together. So I'm going to put this one up again. Maybe we need that. No, we don't need that anymore. So let's push it up there and take this one out. I don't want to forget that. So please, together, let's do the Mohr circle quickly for this item now. Going down. There is two ways to do it, Mohr circle. Everybody knows that. Chapter 7, 1 and 2 shows you doing it through the equation. Chapter 7.4 or 7.3, I don't remember, showing it doing graphically. Everybody understand. In this class, you need to learn graphically because it's much faster and much cleaner to do it because we have to do lots of Mohr circles. So please be careful what we are going to do there. Let's, that one, let's turn it off at the same time. Okay. All right, so here is the problem we want to handle together. So let's see what I did for the other class. So I do the same thing for you guys as well. So, okay, so here we go. This is the problem we want to do Mohr circle for with the graphical. This is the state of stress. Remember, the state of stress comes from chapter 1 to chapter 6. So let's say that we have a sigma x given 12,300. Let's change that to KSI, 12.3 KSI. All right, guys, 12.3 KSI. Then we have a sigma y compressive stress of 4.2 KSI. And then we have a shear stress going negative. So here is the shear stress going like that, 4.7 KSI. Let's say that we are designing part of an instrument, and we end up with this state of stress after we're going through everything that we know, chapter torsion, bending, all sorts of things. Is that correct or not? Transfer shear, it's a normal stress, etc. Correct? And suddenly, these are the questions you want to answer. Okay, if this is the state of stress in part of a structure, and you want to calculate principal stresses, comma, maximum shear, plane of principal stress, PS, I call it principal stress, let's just use it. And plane of maximum shear. And finally, find the stresses. This is something we didn't do for ME218 or run out of time. We want to find stresses at theta equal to minus 15 degrees. Remember one method I just already explained it to you. Answering question number 3, I can use equation 5, 6, and 7. Remember that? Yes? That was the stresses in different direction. Yes? All I have to do in that equation, put theta equal to minus 15 degrees. Remember that? I just was on the handout. Correct or not? However, can we do that with a Mohr circle?
Yes.
Yes. Some of you already know that. I ran out in my class in ME218. I said, well, that when you have the equation, for time being, use the equation, but we can do it with the Mohr circle. And some of you already know that. Is that correct or not? Here we have to do a lot of it with the Mohr circle. Correct or not? So all of this achievable. Now, how do we do that at once? With equation, one without the equation. Let's go graphical. Now, in graphical, you have to be careful about your sign convention. This is sigma, and this is tau with little arrow here. If the shear goes in this way, we put it here. If the shear goes in that direction, we put it here. In other words, this is plus and this is minus. That's how the Mohr circle is going to be constructed. Yes? All right. Now, notice what we have here. Depends where this point is. This could be x and y, because the way I explain it right now, these are x and y. So what is sigma x equal to? Sigma x equal to 12.3 KSI. Sigma y is equal to minus 4.2 KSI. Tau xy is minus 4.7 KSI. Is that correct or not, according to our sign convention? Yes? This could be different. I mean, don't get me wrong. In future problem, I could call this whole y and z, because you are in different plane. Everybody understands. But that does not change the nature of the problem. Still, you do the same thing. Is that correct or not? You just call it y and z instead of x and y. Is that correct or not? Now, graphically, this is sigma, this is the tau, this is positive tau, this is negative tau, this is positive sigma, this is negative sigma. This is tension and compression, and here we go there. Now, we have two planes here. This is the idea here. This plane is perpendicular to the x. It has a normal stress and a shear stress. This plane is perpendicular to, it has a normal stress and shear stress. Those are on the circle, yes or no? Because we said when Mr. Mohr constructed the circle, all the stresses from 0 degree to 180 degree was on the circle, yes or no? Including x and y. So how do I find those 2 points? All I have to plot it. Remember, if I have a point here, don't forget, this point has a sigma and a tau, yes or no? This is sigma, this is tau. Since those planes have a sigma and tau, therefore each plane here will be a point there. Is that correct or not? Which is the plane? X plane. X plane has how much sigma? Look at it. 12, you go 5, 10, 12.3, yes or no? So you go by a scale, 12.3 on the sigma side, yes? Now comes to the shear. Now this is the key here. The shear for us is negative and, for us is negative and, look at it, minus here, it is minus 4.7. That's the way we express that. But for Mohr circle, one of them is positive, one of them is negative. Now there are different book, different scenario. I don't know how your instructor do, but doesn't make any difference. You can put the positive on top, negative on the bottom, or positive on the top, negative on the bottom. But this is the way I used to. This is the way I did it for ME 218. So I'm going to that. This direction I put it on top, which I call it positive. This direction I put it on the bottom, which I'm going to call it negative. Now, which way does it go? Is this goes with the top arrow or lower arrow? Look at it. This goes with top arrow. Therefore, it will be considered positive. Is that correct or not? So that is 12.3. And then positive, how much? Positive 4.7. Yes or no? So that is where the x is. Has a coordinate of 12.3, 4.7. That is representing these two stress. However, this one is minus and which way that goes? Is it this way or the other way? Is that way? Yes or no? It's going that way, yes? Correct? So therefore, it would be negative. So the other one is minus how much? Minus 4.2, that's sigma. And then I have to go the same amount, 4.7. So this is 4.7. This is minus 4.2. That's 12 there. This is y, which has the coordinate, let's put it this way, y, the coordinate of minus 4.2 and minus 4.7 because of this arrow and arrow. These two are on the circle. So if I draw this line of xy, that would be one of the diameter of the circle, yes or no? So if it is symmetrical with respect to sigma, so if I do that, oops, this is in a scale, of course, this will be the center of the circle, yes or no? Yes? Correct? Now, can we do that without reference to any formula? Yes. Look what happened there. What's this total length, guy? Get your calculator. Give me this total length. Come on, get. This length was how much? 12.3. Some of you, one of you. This was 0.2 and add this to 4.2. What's the total length from here to here? Half of it, how much is it? 8.25. So this length, because this is symmetrical triangle, look at it. These two are symmetrical. So this is 8.25. This is 4.7. Yes or no? That's all you need. Everything that you want to know about all those equations is in this triangle. That's all you need is this little triangle. Everything. All the equation, all those complex equations. There is right there. You don't need anything else except this little triangle. Isn't this the radius of the circle? If this is the center of circle, yes or no? So it is 8.25. What is the sigma average? Look, this is sigma average. OC is sigma average, yes or no? Is that the center of the circle? Remember what I said? What is this length? This is 12. Get your calculator. 12.3 minus 8.25. That is 4.5. That's your sigma average. You see, I didn't use anything. It just came out by itself. Is that correct or not? But look, if you add these two together, 12.3 minus 4.2 divided by 2, you get 4.05. Is that correct or not? Nothing. No formula. Everybody see that? And I will ask you to do that in the final. I mean, this is what I was saying to the other class. Everybody laughed that. In one occasion, we went through the Mohr circle in my class in ME 218 for 1 week. I asked the student not to use the formula, or I gave them one student remember all the formulas. I don't know how he did it in 1 week. Remember all the formula. I don't know. He remembered equation 5, 6, and 7. I didn't give it to them. He used it. I don't know how. I don't know how he did it, but maybe had it somewhere there. I don't know, whatever. But it is very strange because I don't remember it. I have to look up to see what those are. Who cares about the equation? And this is the technique I'm going to use in this class. You don't need to remember any equation. You have to learn how to use those tools. Everybody understand? The tool will be given to you. Please do not remember any equation or any formula. Our task is to learn how to use those. Is that correct or not? Nevertheless, as you see here, this is the center of the circle. So sigma average will be OC equal to 4.05 KSI. R, what is the R? Look at this. This is your R. Is that correct or not? Yes, you don't need any formula. R equal to actually 8.25 squared, because this is the right triangle process. A squared plus B squared plus 4.7 squared, so you get your R equal to 9.49 KSI from this triangle. Is that correct or not? Then you draw the circle. Of course, if you can draw the circle nicely, I can't. You put the center here, and this is the radius. You draw a circle. Is that correct or not? For me, it is easier to redraw it here. See, that's the same circle. So you have it almost something like that. So this is sigma. I'm redrawing it. This is the tau. This was somewhere here and somewhere there. So this is something like that. This was your x. This was your y. This was your c. This is your o. Is that correct or not? Yes? Of course, you can do it there. If it is in a scale especially, you can do it. Very nice. Is that correct or not? Yes? Now, what happened here, I have these two. These two are called principal stresses because this is the largest and this is the minimum. So those are become essential part of your design. So this I usually call it A and call it B. We can call it principal 1 and principal 2. Please call it like that because in next handout that I give you, they are represented not with A and B. They are represented with principal 1 and principal 2. Everybody understand that? So therefore, which is the same thing as I used before, but sigma principal 1 or sigma A in this case is sigma average plus R. In other words, this is OC plus CA. So that is equal to OA. Notice the OA length represents one of the principal stresses, which you can add it together, 4.05 plus 9.49. So it becomes equal to 13.54. I'm going 4 digit. KSI, as you see, it is much larger than where we started with. Where did we start with? 12.3. So this is the largest sigma that I can get at that point. Is that correct or not? Yes? And sigma b or OB, which is sigma b, which is the other principal stress, is sigma average minus R. So obviously you can calculate that one is minus 5.44. Now what is the R? R is, you see here, what's the maximum shear? You see you need these 2 points as well. Is that correct or not? Yes? Because of this being a circle, the highest point, the highest shear is the radius. Is that correct or not? This is the good news. The bad news that in Thursday that's going to change. Yes, this is not always the fact. You think it is the fact. That's why we have to understand this to go into the Thursday lecture. Everybody understand that. Otherwise, you do not get the idea how this happened. This is why I asked you to do 1 page of it in color, because it shows you all the circle. There's not 1 circle. There are 3 circles there. Everybody understand. Now let me finish this. I'm not done yet, so just give me a couple of minutes. So R equal to, for tau max equal to, here equal to R equal to how much? Equal to 9.49. By the way, this is called in-plane shear. Get used to it. We have in-plane shear. This is in-plane shear. It's true for this problem, but there is a reason for it. But many times it's not true. Everybody understand that. This is in-plane shear. We call it something new, which comes in Thursday, which is out-of-plane shear. That's why I changed your syllabus a little bit. I put that for week 7, but then I thought there are, so don't put your book aside. I have still 2-3 minutes. You see, I have to push as much as I can. I cannot go back again to this problem. Now, can I find the direction of that one? You see, I have the maximum shear and maximum. So this question will answer, yes or no? Yes? Now, how about this question? Let's finish that, then I'll let you go. I put the last one next time. Is that correct or not? Yes? Where are the direction of that? It's there. Is this, that's what I want you to know, guys. I go with the color coding. So this is very important to recognize. Actually, if you forget about that, this is X and Y. Where is X and Y? X and Y. It is black. Is that, that's the black state of stress. So actually, X and Y is not here. X and Y is there. Yes or no? But look at this. This angle is how many degrees? 100. What's that angle? Why? Because of that change of the sign that he did, Mohr circle did. This was 2 circle, half circle like that. He opened it up. Therefore, write it down in your note if you forgot. Every angle on the circle is twice as much than on the real structure. Notice X and Y there are how many degrees there? Everybody see that? They are at 90 degrees. Representation of them here is at, so it opened up. Actually, X and Y like that, it was opened up because of this. I will explain that to you later if you want to. Is that correct or not? Yes? Therefore, if I want to go from X and Y to A and B, how much should I travel? That much. Is that correct? Which way should I go? Clockwise. But is that theta or 2 theta? 2 theta. Everybody understand. Actually, it's right sitting in front of you. You don't have to worry. This is 2 theta p. Because I have to go from X to A. I have to travel that way. Yes or no? And I have to go this way. So this is 2 theta. Do I need any formula? Not at all. This angle, tangent of this angle is 4.7 divided by 8.25. Is that correct or not? So therefore, please write it down. Tangent 2 theta p equal to tangent minus 1 of, it's sitting there, this height divided by this length. 4.7 divided by 8.25, which is the same as your equation, but this is much simpler. So you get that equal to 29.6 degrees, and then theta p become equal to half of that, 1480. And then if I want to go to maximum shear, which is point D and E, I have to travel that way, and that is 2 theta S. 2 theta S plus 2 theta B equal to 90 degrees. Here, theta S plus theta B equal to 45 degrees. Before I go, 1 more minute. Go to your handout. Go to your handout, please. Because find the result. Now, I have done that. I calculate that. I don't have time to plot it, but it is in your handout. That's what I want you to look at. Look at handout. Go to page No, go to last page, page 18. Go to page 18. Sorry to keep you a little because I have to finish it. I don't want to come back. Look at the last problem on the bottom of the page. Do you see the state of stress? That's the state of stress I gave you there. Do you see everybody? Yes? You see that? 1,200, 4,200. Sorry, in pound. I changed it to KSI. Is that correct or not? Yes? What is the next one there? Can you see that? How much is being rotated? You see? That's 2 theta pay going this way or going that way. He had just gone that way. Is that correct or not? You do 2 different ways. Everybody said that's the state of stress for the principal. Everybody see. One principal is how much? One principal is that the correct one? Yeah. One principal is 13,540. Is that correct or not? The other one is minus 5,400. Is that correct or not? Yes? Yeah? And what's the other one? What do you think that is? Shear stress. Everybody understand what we did there? Yes? We rotate that. I don't have time. I don't want to keep it that one. I show you that detail next time. It takes 5 more minutes to do it, but you have to understand what we did there. Now that we calculated 2 theta P and 2 theta S, all we have to do, rotate our x-axis the same way. Everybody understand, either clockwise or the counterclockwise to come up with that shape. So we'll do that, and then don't forget to bring your new handout with you, which is the new ideas. Everybody understand. But we have to spend another 10, 15 minutes to finish this problem, okay? All right, then.